Okay, so today we start our lesson on exponential functions. Has anyone ever heard the term that something's growing exponentially? Yes? When?
Rapidly.
What? A family?
I said rapidly.
Rapidly. Yes, it's exponential functions are functions that grow rapidly. Yes. Does anybody know what types of things might be exponential?
Exponent.
Well, yes, they have exponents in there. Yes, they do have exponents in there. That's the root word of exponential. Tell me about a rumor. Does a rumor...
Tommy said his best friends tell their best friends. And then
Right, and so do you think it's going to go from one person, and then by the end of the day, how many people are going to know?
About 5,000.
A whole lot of people, right?
probably Honky.
And so exponential means that we're growing really big, really fast, okay? And so we're going to look right here. This is the person that is going to start the rumor, all right? I don't know, maybe. That person is going to tell two people, okay? Then each of those people is going to tell two more people. And then each of those people are going to tell two more people, okay?
Hey, how come
So
only two of their faces are or three of their faces are marked out?
I don't know.
Don't be ratchet.
All right, so we have one person here that knows the rumor. Then in this row, how many people know the rumor? Two. And then in this people, how many know the rumor?
Eight.
And then in this one?
Eight.
All right. What we're going to do is we're going to call these cycles. And so look at this little table right here. Okay? In the first cycle, only one person knows. In the second cycle, how many know? Two people know. There's 1, 2. We've told two people. Now, in the second cycle, we have those two people telling two people. What is that? That's 4. Then for the third cycle, these people are telling two more people. That would be 8. What about 4?
16.
12.
Oh, yeah.
This would be 16. You were right.
32.
32.
64.
48. Wait, no.
64.
Is it 64? Do we go to 6?
Oh, no. That's 100.
It goes to 10 for the cycle. So let's see if we can figure out a pattern here.
Add 1, 2 every time.
Are we adding 2?
No, multiplying.
We're multiplying 2. Well, if we've written down, let's say on this line right here, we've written down 4 2s and they're all getting multiplied, what's the easier way of saying that? Using an exponent. Very good, Erin. So if I wanted to say 2 times 2 times 2 times 2, easier, I would say
2 to the power of.
what? 2 to the power of 4. Right here. Then this would be 2 to the power of 5, right? So this one would be 2 to the power of 10. Now, calculator, does it have a 10th power on here?
No, but I'm trying to do it.
Okay,
Press this little button right here up under clear.
very good.
Yeah.
So if we want to do 2 to the 10th power, then we're going to type the 2,
1024.
and then we're going to type the little upside down V that's right underneath the clear key. And then we're going to write a 10. Now mine does this. Let's see. Not all of them do that though. Here we go. Here's one that whenever you do the same keystrokes in the calculator, it looks like this. Okay, what I want to show you here is that you may have one or the other now. You may have one or the other on your test. So just because you get either one of these doesn't mean they're different. This one shows the 2 to the 10th as the exponent. This one also means 2 to the 10th for the exponent. Okay? Either way, when you press enter, you get 1024. Okay? I wanted to just show you the different ways that your calculator might look. All right, so 2 to the 10th is 1024. So tell me about these numbers. Are they growing at a constant rate?
Yes.
They are?
No.
It's going up 2 every time?
They basically multiplying this here.
It's multiplying it by 2. So tell me about these numbers. Are they growing at a constant rate?
No.
No. They are growing, what did you tell me a minute ago? Well, they are growing exponentially. They are growing rapidly. Yes, this number, is it going slow?
No.
It's going fast. It's getting bigger really fast. So this one is getting real big, real fast.
Big. Real.
That is exponential. All right, so now let's take a look, and we want to compare this to what we've already done in the past. We've already done linear functions, and so we want to look and see how that's different. Here we have for 0, remember this is your x number, 0 plugged in for the x would be what? 0, because that's 2 times 0, right? This one, for putting 1 in, would be 2 times 1, and that would be 2, then 2 times 2, and that would be 4. 2 times 3, that would be 6. 2 times 4, that would be 8. 2 times 5 would be 10, and 2 times 10 would be 20. Now look at these numbers. Are they growing at a constant rate?
No.
Yes.
Yes, this is going up 2, up 2, up 2, up 2, up 2. So you're getting, it's adding 2 each time rather than multiplying 2 each time. Okay? And so let's take a look at it. If we look at just the rumor data, okay, we're just going to look at the rumor data. First of all, let's go back to the linear function. Let's write down changing at a constant rate. This was linear. It was changing at a constant rate. A linear function changes at a constant rate, where an exponential function gets real big real fast. All right, so we're just going to take that linear function and put it on the back burner for now, and we're just going to look at that rumor data, okay? Look right here. What does this kind of look like? What have we done in the what have we done in the past? We've done wings in the past, okay? Normally what we do is we figure out the change in x and the change in y. So let's do that. So let's figure out the change in x. Over here it's getting, yes, we're adding 1. Here it's 1. Here it's 1. So it's 1 all the way down, right? On this side we're going to do the change in y. This one's going up by 1, 2, 4,
6, wait,
8, and then 16. Kind of threw you off because it wasn't changing at a constant rate this time. So because this did not change at a constant rate, because it did not change, or it does not change, at a constant rate, it's not linear. Because it does not change at a constant rate, it's not linear. Where most of our tables actually all of the tables that we've been looking at up to this point have been linear because they have been changing at a constant rate. Well, we just decided a minute ago that it was exponential. So we want to figure out how we could tell if a table was exponential. And so let's take a look at how we're going to do that. This time we're still going to change the x. We're going to figure out what the change in x is going to be. It's a 1, just like the other one. But on the other side, instead of doing the change in y, we're going to do the ratio of y. Can anybody tell me what a ratio is?
Ooh.
What did you say? Parts of a whole. And so the common way that we show a part over whole is what? A fraction. Okay? So what we're going to do is the ratio of y this time. All right? We're going to say 2 divided by 1. We're taking that second number and dividing by the first number. And what is 2 divided by 1? It's a 2. Look right here. We're doing 4 divided by 2. What is 4 divided by 2? What is 8 divided by 4? 16 divided by 8. 32 divided by 16. 2. Notice how we're taking that second number of the 2 that we're looking at, the second number divided by the first number. Look at the ratio. Tell me about them. They're all the same. Yes, they're equal. It's a common ratio. So because this has a common ratio, it's exponential. So that's how you can tell if something is exponential or not, if it has a common ratio of y. And actually, we need to put of y in there. If it has a common ratio of y, then it is exponential. We'll talk about what that equation looks like in just a second. So if we were going to compare exponential functions to linear functions, let's talk about the difference. Exponential functions, what did we do? What did we do? We multiplied by 2 each time. What did we do in linear functions? We added by 2 each time. So, exponential functions involve repetitive multiplication rather than addition like linear ones do. So exponential functions involve repetitive multiplication, where linear functions involve repetitive addition. Okay, so let's see what they look like as a picture.
Yes.
It says sketch the graph of y equals 2 to the x power. So let's go ahead and go to, since it says y equals, we're going to go to the y equals in our calculator. Everybody do this with me. Go to y equals in the calculator. And we want to type in 2 to the x power. Type in 2 to the x power. How would I see the picture?
Graph?
You press graph, exactly.
And then zoom out.
You don't even have to zoom out. You're just going to look at it just like it is. All right, so tell me what the graph is doing on the left side of the y-axis. Do you see that it's still there? Do you see that there's a line there? What is it doing?
Right.
It's getting closer to the what?
0, origin.
What is this thing called?
X.
It's getting close to the x-axis. So I'm just going to tell you, it kind of looks like it touches it, but it never touches it. It gets close to the x-axis, but it never touches it. This is what an exponential function looks like. It gets close to the x-axis, but it never touches it. And if you read from left to right, then is this growing or is it decaying?
Growing.
It's growing. So this is called exponential growth. And we're going to call this graph A. Now let's go ahead and sketch the graph of the next one. We're going to do 3 to the negative x power. 3 to the negative x power. And we're going to press graph to see what that one looks like. Describe this one for me.
It's decreasing. Never touch the X thing.
Okay, so it's kind of flipped. It's backwards. It's starting really high, and then it's getting closer and closer to the x-axis, but it's not going to touch it. And so the options are growth and decay. Which one is this one going to be? Decay, because it's decreasing. We're going to call this graph B. All right. Now let's go and do that last one. Notice you have parentheses with a fraction in it. Go ahead and type it just like you see it. It's 1/4 to the x power. And let's press graph on that one. Which one does that look like?
Decay.
It looks like the decay one. Well, we need to compare these so we can understand what made them do what they did. Sorry, that graph was a little off. So this was a decay, and this we're going to call this C. Okay, so look at these two first, graph A and graph B. Can you tell me in the equations what made it go from growth to decay, Erin?
Negative.
The negative what?
Exponent.
The negative exponent. The negative exponent made it decay. It went from growth to decay because of the negative exponent. All right, well, I don't see a negative exponent on graph C, but it's still a decay model. What do you think made it decay this time?
Fraction.
The fraction. Now, the fraction is not an exponent, is it? No, it's the what? Do you remember what it's
Whole
called?
number.
The base. Good. The base, the fraction base, made it decay also. So the fraction base made it decay. So let's look at what we just said in words. It says when the exponent is positive, then it is exponential what? Growth. When the exponent is negative, it is exponential decay. What does decay mean?
To decrease.
Decrease, okay? When the base is between blank and blank, then it is exponential decay. So we're talking about
0 and 1.
0 and 1. Very good, Lawrence. The base is between 0 and 1, then it is exponential decay. What graph is this one, the exponent being positive? Graph A. Exponent negative was graph B, and the base being between 0 and 1 was graph C. Now look at each one of these and notice that each one has a base. This one has a base of 2, a base of 3, and a base of 1/4. Each one has an exponent. This one has an x, this one has a negative x, and this one has an x again. But what do they all have in common for exponents? They all have x for an exponent. Just so happens that this one's a negative x, right? So an exponential function, this is what an exponential function, this is the general thing for an exponential function, general equation. Y equals the b, which is your common ratio, that's your base. The b is the common ratio. And then the variable is the exponent. The variable is your exponent. So let's go back and write an exponential equation, an exponential function for the rumor data. So look right here on this one. If we said that it is y equals b to the x power, what did we say the b was? That's the base, and it is the common ratio. What was our common ratio on this problem? It was a 2. So our base is a 2, and the exponent is x. So this is the exponential function for that table. Y equals 2 to the x power. Because we put our common ratio to the x power. Okay? So, the next one, the next part says, determine if the table represents an exponential function, and if so, what is the common ratio? How can we determine if it's an exponential function looking at a table of values?
If it's a function first, x don't repeat. Right?
Okay, very good. So we know that it's a function if x doesn't repeat. How about exponential?
If you have a common ratio.
if you have a common ratio. So let's write that down. If you have a common ratio, then it is exponential. All right, so let's look at the first one. Remember, we're putting our ratio of y here, not the change in y, but the ratio of y. So we're looking at x. This one goes up by what? 1 here and here. How do I do the ratio? And how do I write it? How did I write it before? Let's look back. What did I write? I wrote the second number on top of the first number, right? Second on top of the first. So 13 over 10. Put that in your calculator and get me a decimal answer so it's easier to compare them. 1.3. Okay, look at the next one. What's the next ratio going to be? Good. 16 over 13. Is it 1.3? Put it in your calculator and see.
1.2.
It's 1.2. Look at the next one. 19 over 16. 1.18. Are those a common ratio? Are they exactly the same? No. This one does not have a common ratio. So what? So it's not exponential. Because it does not have a common ratio, it is not exponential. Okay, let's look at the second one. And before we do this one, I need for you to change the numbers on it. I need this to be a 9, this to be a 12, and this to be a 16. And so again, we want to see if it has a common ratio of y. And so what numbers would I write for this one? 12 over 9. Put that into your calculator and tell me what you get. 1.3 repeating. And then how about 12? This one is going to be 16 over 12. .3 repeating. So does this one have a common ratio? Yes. This one has a common ratio. What is it? What is the common ratio? 1.3 repeating. So it is exponential. This one has a common ratio of 1.3. The reason I put the 1.3 on here is because it told us to. It says, what is the common ratio? It is exponential because it has a common ratio. All right, so next one. It says complete the table and graph. So let's do that. Let's take it and put it into our calculator. Y equals 3 to the x power. And remember that there is an online graphing calculator on Blackboard. On the left-hand side under the tabs, there it says online graphing calculator, and you can type these in and look at a table and a graph in there also. Let's go to the table on the calculator here. 0 would be 1, 1 is 3, 2, 9, 3, 27, 4, 81, and 5, 243. What if I did not have a calculator? What could I have done? Well, not mx plus b. Look at your equation right there. We could have plugged in the x number for the exponent. So this would have been y equals 3 to the 0 power. That would have been 1. 3 to the first power is 3. 3 to the second power is 9. So you just plug in the values if you don't have access to your calculator. Okay? Let's go ahead and graph this. 0, 1, 1, 3, 2, 9. Okay, so this one appears to be exponential. If I just connect my points here, have I made a good graph? What am I missing?
It don't matter.
The part where it's getting what? Closer to the x, right? I need the part where it's getting closer to the x. And I also need an arrow showing that it's going to keep going forever up. Okay? And you can check that by looking at your graph. Now we want to talk about what the domain and range are of this function. Domain is what letter? That means range is your y. Remember that domain, we want to know what values of x does this graph include. So if we take our pen and we go along the x-axis, will my graph continue to go in this direction? Yes. Even though it's going really small, will it continue to keep going in this direction? Yes, because you can see that it's kind of moving out a little bit, it's going to keep on going in on the right direction as well, going to the right. So that means your domain is what? All real numbers, because it's going to go to the left forever, it's going to go to the right forever, okay? Now let's look at the range. The range is your y numbers, okay? Remember, y is going up and down, so will it go up forever? Yes. Will it go down forever?
No.
No. Where does it stop? On the what? On the x-axis, right? But we're still talking about the y numbers, right? So the x-axis represents which y? 0. It's where the y is 0, right? Will it be exactly 0? No, because it's never going to touch there. So this is just going to be y, and then how do I show going up forever? Greater than 0. Y is greater than 0. We have one more here. It says, which function best describes the data given in the table? There's a couple of different ways that you can do this. You can look to see if it has a constant ratio or constant rate of change or a common ratio. You could do that. You could also type these into your calculator and see which one matches this table. You could plug in the x's to each one of those and figure out if your y values match it. But I want to do a process of elimination with the answer choices. Okay? What do you know about a squared exponent?
It's gotta be 8, right?
It's quadratic. Very good. It's quadratic. What does quadratic look like?
U.
It looks like the U, right? It's not going to look exactly like that. So is this, and look at this table of values, what's it doing? It's getting higher faster, right? Look at the numbers. They're growing what? Exponentially? Yes, they're growing exponentially. We can figure this out by finding the common ratio. This one's quadratic. It's not going to do that. Okay? Look at this one. This one has a negative x. What did we remember about a negative x for the exponent? It makes it decay. Is this one getting smaller? No, it's getting much bigger. Look at letter C. So these first two did not make it. How about the next one? The squared. It's quadratic again. No, that's not working. Look at the next one. It has just a plain x. If you plug in your numbers, let's do a double check. 3 to the first power is 3. 3 to the second power is 9. 3 to the third power is 27. Okay? So D is going to be our answer. Let's look at this one in the calculator. This last one, we're doing negative 3 to the x power. And let's press the graph button. Negative 3 to the x power. What did it do? It flipped the exponential down. So that's not it either, because it's increasing. Our table is increasing, and this is decreasing. Okay? So D is your answer. Are there any questions about exponential functions?